So I'm going to talk
No,
about
this
the
is not
autonomic
nervous.
nervous
You're
system.
seeing
I'd like to talk about
Sorry,
how
and
to
what?
approach
No, why?
endocrinology for your
You're
physiology
what
classes as well
amazing.
as for a
What
lot of
the hell is
medical
going on? How
exams.
come
We are
has
going to
go
get through
over,
this table
everyone?
in a way that makes
This is
sense
Emily
so you
Nora
don't
here.
have to
We're
memorize it,
feeling
because you're going to need it, guys, for all of these exams and a
Maybe
whole
it's
lot more.
hallucination.
As always, I'm going to
Neglection.
ask for your support.
Guys,
If you
I've
could
just
take just a second and
it's
click those buttons
actually to
if you
do
find
it.
these videos helpful.
Something is
It makes a
completely
big
wrong,
difference
guys.
on my
It happens
end.
at first, whatever.
Some knowledge that I'm
There's
assuming
the
here,
video right there.
knowledge
This
about
is
polar
not good,
molecules
guys.
and how they interact
There's
with
a
the cell membrane.
hallucination. No
If you want to know more
collection.
about the structures, the
There's
chemical
a
structures I'm
guy.
going to show, I have a video there.
Recycling.
And
Your
this one's
thoughts are
probably the most
harmless
important
right
signal
there.
transduction. I am
Just
assuming that you
regular down
understand a little
there.
bit about
You
how
have to look.
ligands
What
and receptors work.
Oh no, there's
As
something
always, I have
there.
the links down below. Now,
What
we are
happens?
talking about an
Why
aspect of
is
cell-cell
this half
communication when we talk
all over?
about
We
endocrinology.
going to
But
do
to take a
it.
step back
You're
for
like
just a
this.
second,
It's been over
cells
12
can
hours.
communicate
It's
with
like
other
that
cells
I
that are
put
close
every
by with
aspect
gap
of our
junctions
life
and
on. It's
contact-dependent
what happened.
signals
We have
and
this
paracrine and
forever.
autocrine secretions.
Ever.
For
Since like this here right
long-distance
there. You're
communication,
getting
we've
here.
got a
The
couple
community
options.
has
We have the nervous system,
community has place
and
their
you've
God.
either studied this already
There
or
is
it's
some
coming,
mystery
where
of
we have
science.
neurons
The
that
last
produce
half over.
neurotransmitters and
There's
cause a
seeds.
response in a
Is
target cell.
there a word
In
here?
the endocrine system, we
There
have
is
secreting
a
cells that
cut
produce
the box
molecules
of
that
the
are
plate.
carried by the
You're
blood
talking
to
over
distant targets.
here.
And cells
There's
that
a
have
right there.
receptors
Oh,
for these
that has
molecules
all over
will
place.
get a response, and cells without
You
receptors are oblivious to the
We
signal.
have you all
Neurons
here
play
at
this game
place.
too,
You're
by the way,
having
and
a
neurons
dish
can
in the
secrete
world
molecules that go directly into the
So, what
blood,
is the thing
endocrine
that
style,
it
and
so,
same kind of response. If the target cells have receptors for those molecules, then you get a response,
so
and
nutty.
cells
Your
that do not
hands
have
off.
receptors don't.
You're
Now,
all
the question that I
happy.
want to address in this video
No,
has
take
to
your
do with
time.
how
Actually, you're
hormones
not
do their
liking.
thing.
If you like
In a
your
traditional
hands off.
anatomy
I don't like
approach,
it.
you end up having to
What's
memorize
going on?
all of this stuff, and it
My
really is a
feet hurts
nightmare. I
anymore.
propose that a
Why do I
chemical
have your ear?
classification
No,
is going to be
you know,
much easier
someone-
when we start talking about the function of these things. And when you talk about chemical classifications, there are only 3 categories that we have to worry about. I don't know about you, but 3 is a lot more manageable. So we're going to talk about all 3 categories and answer these kinds of questions. These are very typical questions that you're going to see on a lot of exams. There's only one fundamental question that you need to know the answer to when you are approaching things like this. And that big question is, what kind of ligand is it? Is it polar? That is, does it fear lipids? Or is it non-polar? Does it love lipids? If you know the answer to that question, you're going to be able to talk about how the hormone moves through membranes and how it dissolves in the blood. So if the molecule is polar molecules don't pass through membranes easily, but they dissolve in the blood because the blood is mostly water. If the molecule is non-polar molecules love membranes because they are very, very lipophilic, but they have a hard time dissolving in the blood. And ladies and gentlemen, that is it. If you know what kind of ligand it is in terms of polarity, you're going to be able to very easily predict all kinds of things about the hormone's behavior. So here's a simplified view. We're going to look at polar and non-polar ligands, and then we're going to look at the 3 different categories of hormones, which are just different examples of these 2. So we have the secretory cell on the left, and you can store polar ligands in membrane-bound vesicles, no problem. When it is time to release them, you get exocytosis, and here we have the little polar ligand being exocytosed, and it dissolves very, very easily in the blood and can be carried around the body. However, when it comes time to affect a target cell, because it's polar, it doesn't move through the target cell membrane. It has to bind to a surface receptor, and you'll get a signal transduction mechanism, and that is how the molecule exerts its effects. On the other hand, if the ligand is non-polar, then a secreting cell can't store it in any kind of membrane-bound vesicle. So they're just made as they're needed, and they will diffuse through the membrane very easily. The problem that non-polar ligands have is that they don't move very easily in the blood. They are going to require a carrier molecule. and we'll get to see what those look like. They are
There's
so
wires.
cool.
There's
In
wires
terms
that
of the
go to
target cell, because they're nonpolar, they can diffuse right through the cell membrane and bind to receptors either in the cytoplasm or in the nucleus. So you're going to get these kinds of questions for any given hormone that they're going to give you. They're going to ask, how is it made and stored and released? And the answer depends on whether it's polar or not. If it's polar, you can make those ligands in advance and store them and release them by exocytosis. If it's nonpolar, you can't. You can't store them because they dissolve right through lipids. So they're made as needed and they're released by diffusion. Another question, how are they carried in the blood? And what's the half-life? Again, is it polar or not? If it's polar, it's going to dissolve in blood plasma, no problem, but it doesn't last very long. It's going to have a short half-life. If it's nonpolar, it requires transport molecules, and it will have a longer half-life. It's almost like those transport molecules protect the ligand from degradation.
Take a look at this.
You're going to have to know how the hormone enters target cells and where the receptors are. Again, if it's polar, then it can't enter the cell directly. It's going to have to bind to a surface receptor. If it's nonpolar, it enters the cell easily and will bind to either cytosolic or nuclear receptors. What's the cellular response and the lag time? Again, is it polar or not? If it's polar, usually the hormone will cause modifications of existing proteins. Signal transduction mechanisms usually do that. If it's nonpolar, usually you're going to look at induction of new proteins in the target cell, and that takes a lot longer. So you're going to have a higher lag time. Now we can look at all three classes of hormones and see what they do. Peptide hormones are first. There are a lot of peptide hormones, so I just gave you a partial list so you can look through it and see many of the hormones are probably familiar to you. All of them work this way.
Get in here.
All peptide hormones are polar, so they cannot pass through membranes. They will require signal transduction, but they dissolve very easily in the blood. And hopefully now this makes some sense. Peptide hormones are made in advance. They're released by exocytosis. They dissolve in the plasma. They don't last very long, and they require a cell surface receptor where they cause signal transduction and the modification of existing proteins in the target cell. How cool is that? Let's look at steroid hormones next. Steroid hormones are all made from cholesterol, and they have a lot of roles in the body. And I'm showing a biosynthesis pathway just so you can see some of the steroids and how they're interconverted one with another. Steroid hormones are non-polar, so they pass very easily through membranes, but they do not dissolve in the blood. They're going to require carrier molecules. Now, I want to show you some of these carriers because they are really interesting, and I think they'll give you a sense of how steroid hormones sort of are in the body. These protein carriers include SHBG. These are sex hormone binding globulins, and they are found, interestingly enough, in all vertebrates other than birds. That's interesting. We also have transcortin, which transports progesterone, cortisol, and other corticosteroids. And steroid hormones, as a result of being, in a sense, protected by these molecules, they have a very long half-life. I want to take a minute and show you what some of these molecules look like because they are so cool. So let's take a look. All right. These images were generated by PDB, that's the protein database, and I have the unique identifier at the bottom. So you can go and play with this yourself. So what you're looking at are the two subunits of SHBG, and what we're going to see, I'm going to stop rotating it, and here with the white arrows, you can see the estradiol. The green arrows are pointing to calcium ions, and you can really see there's the estradiol again in a different view, and I hope you can see how protected that steroid hormone is. Let's look at just one subunit so you can see it a little bit better. So here's the estradiol kind of hidden inside. It really is like a protective barrier that allows this thing to be dissolvable in blood plasma. Let's rotate it a little bit. Gosh, that's so cool. Look how protected that thing is. Also neat that you can see that calcium ion and how that affects the shape of the entire structure. I think this is just amazing to really see how cool these things are. There's the estradiol one more time, and the calcium hormone.
More has long. I have
Okay, that is just so awesome. So now when you see these little cartoons and you see steroid hormones in the blood in these little boats, now you have a sense of what it really looks like. Now, steroids can move right through the target cell membrane, and they bind generally to receptors in the cytoplasm or in the nucleus. So let's go ahead and fill out our table, and you can see that, gosh, it's because they're non-polar. They're made when they're needed. They are released by diffusion. They need those carrier proteins to be transported in the blood. They last a long time, and they bind to receptors in the cytoplasm or in the nucleus, where they usually induce synthesis of new proteins.
More like
finally, we have amine hormones. Let's look at amines. Now, when you see the word amine, it should make you think of amino acid. That's exactly where they come from. Tryptophan is the source of melatonin and serotonin, and tyrosine is used to make the catecholamines and the thyroid hormones. So here's tryptophan. Tryptophan is tweaked a little bit to make melatonin, which makes you sleepy, and serotonin, which makes you happy. That's my personal favorite. Here's some biosynthesis pathways, just in case you are curious and you want to see how similar some of these structures are. Here's a little simplified view. Tyrosine is converted to the catecholamines in neural tissue. Dopamine, epinephrine, and norepinephrine. Now, how these amines work is based on their polarity. So they're polar, they can't pass through membranes, but they dissolve easily in the blood. Do you see the pattern here? Yes. They're made in advance and stored. They're released by exocytosis, where they can dissolve very easily in the plasma. They don't last very long, and they require cell surface receptors and signal transduction mechanisms to exert their effects. These are also amines, but thyroid hormones we treat separately because they are a little bit different. So T3 and T4, we're talking about molecules that mainly regulate metabolism. They're synthesized like peptide hormones, but they behave like steroids once they're released. So this is kind of tyrosine is converted to T4, which is then converted to T3. Now, students always ask me about the T4 and T3. The numbers are just, check it out, the number of iodine atoms in the molecule. See, the structures actually help you. Just how many iodine atoms there are. Now, what's interesting about thyroid hormones is that they're made in advance because the precursors are polar, so they can be stored in vesicles. But as they get a signal for release, they're tweaked a little bit chemically, and then they become non-polar. So their release and transport, half-life, etc., all of that is like a steroid. So that's what makes thyroid hormones a little bit bizarre. But again, once you understand that the reason is because they're made as polar molecules, but they're released in a non-polar form. Gosh, it all makes sense. So now we have the completed table. And what you should be able to do now is make a table like this for yourself and see if you can fill it out on your own, just knowing which of the categories are polar and which are not. And that's the secret to understanding what the heck these hormones are doing.